Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. What we started out last class, we looked at viscous dissipation, we looked at production, right? So I'm kind of, almost going to do a little recap of that. Okay, it's worth sort of going over it a little bit. Okay, so what we were looking at, we first sort of talked about viscous dissipation. So this is for a round jet, okay? Now, for example, this is from the Navi-Stokes equation. This is an equation that we wrote down, right? This is the flux. Right, and where this Sij is the rate of strain tensor. Okay, let me write that down. Okay, this is the rate of tensor. Okay, that is right. So we looked at this equation, right, and then we integrated this. We integrated this, right. We took an integral of that, and we found that the right hand side, right. So if I take an integral, right, of the right hand side, okay. If I take an integral of that. Now this term, so this, okay, so then we can write this term is essentially well, what I'm trying to say here is this term is always positive. This term is always positive, right? This is always positive. Therefore, this integral, right, which is essentially the total energy, right, due to the viscosity component, right, is negative, right, and therefore we said this, we equated this to what we called as a sink, right. So what are we talking about here, right? We said we had several sizes of the eddies, right? The energy was being transferred, right, from the larger eddies to the smaller eddies, right? And how long was this going to go on? Till we found a size which was small enough where further transfer of energy was not going to happen, right? But then what was going to happen to that energy? Now, energy cannot be destroyed, energy cannot be created. What is going to happen to that energy? Now, that energy is going to be converted, right, to heat, which is basically internal energy, right? So, when we had larger eddies, okay, we had larger eddies, and we looked at the length scales at which this was happening, right? We looked at the Kolmogorov length scales when this sort of thing was happening, right? We wrote that down, and this was happening over also a range, right? It's not going to be sudden that suddenly it goes from mechanical transfer of energy to suddenly becoming heat. So that was happening over the internal range. What was that thing that we said? Okay, the inertial subrange, right? So now what was going to so this, when we have larger eddies, okay, there is the transfer energy, right, to smaller eddies, right? And how long is this going to go on, right? Till we reach a length scale where this is not going to happen. Then what is going to happen? I still have energy, right, to account for. So then at that time there is the energy, so to smaller eddies. So this is essentially, this is mechanical energy, right? So you have fluid particles moving at different speeds basically, right? So now this mechanical energy is going to be converted to internal energy, essentially internal energy, or as we say, heat. Right? Now this happens because of the viscosity involved. As you can see, this is the viscosity component that we're talking about, and hence this is essentially called as the viscous dissipation. Right? So this results in essentially the viscous dissipation. Okay. Then the next thing that we did is we took a mean of this equation. We took a mean of this equation. Let's do that again. Okay. So we have something. Okay. Right? Now if I take a mean, simply I take a mean of this, right? So essentially what I'm doing is right, and let me write it this way, which I think I didn't write yesterday. I take a mean of this, right? Now the right hand side again, okay, now this is the side we wrote this, right? We wrote this as well, I don't know if I don't remember if I wrote it this way. If I didn't, then just take note of that, okay? Now, so this is a mean value. So what we mean by that, what I mean by that is that, let me first write this down. So we wrote it this, we just took the mean value, right? Now again, I'm working on the right hand side of this equation, right? And this epsilon, this is nothing but this, right? And okay, so the right hand side, I'm just sort of breaking it down such that I'm representing it. What epsilon mean essentially is just the mean, all right, of the rate of strain tensor, right? This is also the same. What is the difference between the epsilon and the epsilon dash? Basically, as you can see, that this is the mean component of the velocity, and this is the fluctuating part of the velocity, right? So therefore this here, this I think as we wrote down, this is the mean of the rate of strain, right? This is the rate of strain basically, and this is the mean of the fluctuating part of the rate of strain. Okay, this is also a mean of the fluctuating part of the strain. Okay, so what essentially we did here is that we just took a mean of the Navier-Stokes equation here, and the right hand side, right, I just wrote this down to sort of differentiate maybe a little bit. Okay, you'll see the reason why. Okay, we did that so that epsilon bar here, okay, which represents this, and you can see that this is essentially epsilon bar is essentially the mean of the rate of strain. Okay, now the dash basically represents the mean of the fluctuating part of the rate of strain. Okay, now, and of course, okay, so I think, so essentially, if I may write this again actually, right, this is the rate of strain is nothing but, right, this that. Okay, and the mean of the fluctuating part of the rate of strain again is nothing but that. Okay, now it has been found, how? Well, by experiments, it's been found that this, right, the mean of the rate of strain, right, so essentially now, as we've seen just now, right, if we integrate this, that the right hand side essentially, right, the right hand side is representing, so this right hand side, right, is representing the viscous dissipation, right, viscous dissipation through which mechanical energy is being converted to internal energy, right, and in that, right, now we see that I can, if I take a mean of that, right, we took an integral of that just a little while back. Okay, now when I take a mean of that and I can write it in this fashion, so essentially what I'm trying to say here, right, is that this part, right, this part, right, is the contribution to that viscous dissipation by the mean flow, right, and this is the contribution to the viscous dissipation by the fluctuating part of the flow. Make sense, right? So what I'm trying to say here is that we are now, okay, so essentially when I took the integral, right, integral of this entire equation, what we're trying to say is what is the total rate of change of energy in the whole thing, right, and that's, so we equated the left hand side to the right hand side, right. So then this is basically telling us the net change in energy. Now that is happening because there is a viscosity property of the body, and this part, if you integrate, then that is essentially giving us the part of the energy which is being transferred due to the physical movement of the fluid across the surface of the domain that we are considering, right, of the control surface. So there is inflow as well as outflow. So there is the net change. So that this is the energy change which is happening because of that, right? And this is the instantaneous change in the energy. So, and the right hand side is due to the viscosity. And we reasoned that the right hand side that is happening because of the viscosity is essentially behaving like a sink, which is essentially telling us that here there is viscous dissipation happening, right, resulting in conversion of mechanical energy to internal energy. Okay, now we did that, and the next thing we're now saying is I just took a mean of this, right? That's it, same equation. All right. Now, if I do that, and I wrote the right hand side in this fashion, right? And I see, so basically all I'm saying is if I do that, right? So if I do that, I see that this term, right, epsilon, right, the mean of that is essentially the mean of the rate of strain, and I can say that this, okay, so this is I'm going to write it here, okay, or say write it here. So this one is essentially contribution, right, to the viscous dissipation by the mean part, right, by the mean component of the turbulent flow, right? Makes sense? And therefore, this one on the other hand is the contribution to the viscous dissipation by the fluctuating part of the, so this is the contribution by the fluctuating part of the fluctuating flow, fluctuating part of the turbulent flow essentially, right? And it has been found that this, right, depends on inverse of Reynolds number, and if you have high Reynolds number, then this is something which can be negligible, right? So we can omit that. So that makes a very good, very important inference here, which basically is saying that viscous dissipation right, is primarily due to the fluctuating part of the turbulent flow. Yeah, so viscous dissipation is basically dominated by the fluctuating part of the turbulent flow. Okay, right. So now, and this was about the viscous dissipation, and yeah, so essentially that. Now, then the next thing we had spoken about is the production. Now we took that equation, right, and we wrote it. So the same equation that we just saw, right? When I write it like this same, the mean equation. Okay, if I write it like that, now so I'm going to do this here. Okay, so now let's take sort of this equation here. Okay, and so E is essentially fluctuating part, the mean part and the fluctuating part. Okay, same with the flux, mean and the fluctuating part, right? And the epsilon, which is on the right hand side, right? So that we again write as a mean and a fluctuating part. Okay, so then we have the equation, which is S this, or let's just say basically this is equal to epsilon, right? So then let us just replace all of these by saying, I'm going to write this as mean and a fluctuating part mean and a fluctuating part okay, is equal to a mean and a fluctuating part. Right? I can write that. Then I get those two equations which we wrote down last time. So then we wrote this down. So d dt, right? The mean this, right? And then we write that. Okay. Now to this we did, so then I just broke this down. So if you add these two equations, you pretty much get back this, right? So this is, so I can say this is actually equal to this equation plus this equation. So if you break it back, it will be same. Then we did something. So then we said vegan 2, that and this. Right? And then we found out that this P, so I'm not going to go to the details of it, which I did last class, but I'm just writing it out. So this we found out to be equal to that, and you take a mean of that. That is the mean. Right? And again, here we found that, this is the contribution to the viscous dissipation. We've spoken about this earlier, right? Then what is this P, right? What is this P? Now this term, okay, it turns out that this is mostly positive, right? This is mostly positive, right? And therefore this is considered to be a source of energy, right? And hence we call it production of turbulent kinetic energy, or simply production, right? So this is the production that we spoke about. So this is nothing but the production. Okay. Now if I see the equation here, so what am I doing? What I'm doing here is I'm taking this production, right? I'm subtracting it from this equation, right? This one, and I'm adding it to this one, right? Now this equation is essentially this one. Let's just call it A, right? And let's just call this B. So I take the production, which is P, right, and subtract it from A and add it to B, right? So when I subtract it from A, what am I doing? The A equation is basically for the mean part of the flow, right? And the B part is for the fluctuating part of the flow, right? So what I'm doing is I'm taking the production, right, and I am taking that and subtracting. So I'm essentially taking out energy from the mean part of the flow and adding it to the fluctuating part of the flow, right? So, or to be more explicit, I'm removing K from the mean part of the flow and supplying that, or add it to the fluctuating part of the turbulent flow, right? So that is essentially what the production is doing. Okay, so I can sort of write that. So it's what the production is actually doing is taking, or say removes. So P essentially removes kinetic energy from mean flow, right, and adds to fluctuating flow. Right? And we also saw that the viscous dissipation is dominated by the fluctuating part of the flow. Right? Okay, so this is something that we kind of spoke about yesterday. Okay, now let's look at the dissipation and these things, a few things, a little more. Okay, now all this while that we are doing all these things, I think the constant question is, how do I measure this? And especially if something is so unsteady. So, again, I think we've spoken about this before. So if you continue, how many measurements are we supposed to make, and how is this going to represent the entire domain that I'm talking about? Lots of questions, right? Now, so this equation, I think I'll write it again. Okay, so this equation here, right? The B part, right? So as we said here, this one, right? So this is the dissipation of the fluctuating part of the turbulent, or fluctuating part of the turbulent K, or is it simply the dissipation, right? If I look at this cloth here, okay. Now, we know this, that profiles of mean flow, right, and fluctuating flow right. If I took functions of these, okay, so these are essentially are functions of, say, zeta, which is, I think we've done this before, if you remember, right? Okay, if you plot essentially. So the point is, if I were to do this, right, you would have this by this, r by r half, and you'll get one plot, right? So you see, I can have several flows like that, okay? But they will all, if you plot this versus this, then it's going to all be just one curve. So that's why they are self-similar. Okay, so similarly, this the fluctuating part. You can have several different types of flows, but if you plot, this value against this, right? If I do that, then you basically get one plot, right? It's self-similar. Okay, so these are therefore, these are functions of this, are self-similar, right, and independent of RE. Right, independent of RE. Now then, right, let's just write it this way. So I'm going to scale the production also. By u naught cubed by r half, right? So production is essentially this, right? This is the one that I'm talking about, this one here, right? I'm going to scale this by u naught cubed by r half, right? So this means what? This if I do that scaling, it means what? Right? Okay. Right? This is what it means. And you know that, so why am I writing it this way? Right? The reason I'm writing it this way is that this, is self-similar. So this one, if I plot against r by r half, it's going to be self-similar. R half by u naught, so this is also self-similar. Okay. Now, again, that now k, right? Now let us say right, the fluctuating part of the kinetic energy. Okay, so this by u naught square, right? So essentially what I'm saying is, if let us just go back to this equation. So if you look at this equation here, what we've just said is that we said this production, we're going to scale that with u naught cubed by r half, right? Now we're going to do the same thing over here, right? We're going to do that over here. So right, so now T of course will scale by u naught by r half, isn't it? So then this one, if I scale, T can be scaled by u naught by r half, right? And K itself I'm going to scale by u naught square, right? So this essentially means that I'm scaling this by u naught cubed by r half this, isn't it? So if you see what, if you look at this equation, therefore if you look at this equation B, right, what I have done is I've basically multiplied this, right, and the P by 1 by u naught cubed by r half, right? And I know that these terms are going to be self-similar. I know that, right? Now if that happens, one can, it's almost, we're almost expecting that if that is true, then even this is going to be, if this also I scale with that, and this is also going to be self-similar. Why are we even talking about these things? Because the point is, even if I solve this, say, equation, even if I solve this equation, it will be in some space and for time, right? But this is a highly unsteady case. Now, why do we need, the self-similarity to kick in? Why do we need? Yeah, it's just that there are too many possibilities, right? Too many possibilities, and I'm trying to figure out which one is right, or which one is actually appropriate to what I'm looking at, right? So essentially, I found out a scaling. It's such that you can take whatever values you want; they will all collapse into one plot. That's why they're self-similar. So if I look at this equation, right? So you have the first term and you have the P, right? These all scale with u naught cubed by r half. Then what happens to this one? I would almost expect that this also will do the same, right? So that's all. It's a hunch that it's just a hunch, okay? And we almost expect that since that is happening, so therefore, essentially, okay, if I take this also, I scale it with this, right? This is also self-similar and it is independent of R. This is my hunch basically, okay? So the good thing is that this was actually confirmed with experiments. It was confirmed actually. The hunch turned out to be correct, confirmed by experiments, by right in the JFM paper 1993. This was the first part, okay, and by Hussain right, that was also in JFM, I think, yeah, right, in 1994. Again, my utmost privilege to have been a colleague of Professor Panchapakesan when he was at IIT Madras. My ultimate privilege to have known him even for a little bit. Okay, so again, this was actually confirmed by experiments by Panchapakesan and Lumley and Hussain. Well, come to think of it, not too far back, right? So, so hence, what? So the point is that we did all these things. We're trying to figure out what is production, what is viscous dissipation. So we spoke about these things we looked at pictures and we said, oh, there are big eddies, so they become smaller. There is an energy cascade. When the energy enters the flow field, where does it enter? It enters into these eddies, which are the largest in size. Right. Now, the largest eddies do not remain so. They break down into smaller eddies. How long does this continue? Till the time we reach a certain Reynolds number and a certain size, such that no more transfer of mechanical energy is happening. Right? Then what is happening to that energy? It is getting viscous. It is getting dissipated due to the viscosity to internal energy. Right? Now the point is, so that's that, right? So then we put that down into the Navi-Stokes equation. We try to think that, okay, so now are we going to be able to actually calculate these things now that we understand? Can we actually calculate this and quantify these and so on and so forth, right? So then we're just playing around with the equations. We're playing around with the equations to see what these things mean to us. Right? So it seems to mean to us, these things make sense, right? The production, the viscous dissipation, etc. The question is, how do we plot all these things, right? So self-similarity is something that it's right from Prandtl's boundary layer theory back in 1903. So we've been using this, and like I said, this was used. I forget the name. So the first time, a little later on. For turbulent studies as well. So we've talked about this earlier. So again, these are values which are, these are functions basically. So these are functions of, or if they scale with r by r half, they're self-similar, they're independent. Okay, we did the same thing with the production. So we saw that. So if I take the production, so that also scales with this. Right, scales with this u naught cubed by r half, and then we saw the first term, which is the rate of change of the turbulent part of the kinetic energy. That also scales with u naught cubed by r half, which basically means that this term and the production, scale production, so these things are self-similar and independent of the RE. Now these are all in the same equation, so one would expect, or one would almost, this is like a hunch, like I said, it's a hunch, that the turbulent part, right? This is the turbulent part. Yeah, so I think I should write that here again. Okay. All right, so let's just say this, okay, right? So the turbulent part of the kinetic energy also scales with u naught cubed by r half, so which meaning that it is also self-similar and independent of RE. Okay. All right. Now we'll look at something more a little bit interesting, right? Now, so the sense that we'll look at two flows. Okay. So I'll give you two scenarios. Now this is one, and this is two. Okay. Let's say the dia in the first case is d. Here also it's the same. Okay, then you got the velocity, which is, say, uj. This is also uj, it's same, right? Then you have the viscosity, right? So this one is, say, nu1, and this one is nu2. This is different, okay? Then you have the central line velocity, right, which is essentially this, and that is also same, okay? And the half width, which is r half, okay? Right, so this is the scenario I have. Now, what did we say the epsilon was, right? We said this epsilon is essentially right? Okay. Now, like we wrote down here, I'm going to just use this. Okay, I'm going to just use that. Sorry. So essentially, I said this. Okay. So then, so let's just say, I'm going to say epsilon 1, right? So it's going to scale. So this is the turbulent part. Okay. So this is going to scale with u naught cube by r half. Okay. Okay. Yeah. So now here comes the point. The point is this term, right? In the sense that if you look at this plot here, right? Now this will give you the same value for different values of epsilon dash, u naught, and r half. In the sense that all of these, when you plot, they will all fall on the same plot. They will fall on the same plot, right? And therefore they're self-similar. So meaning that this will always have the same value, right? So if I do that, so this is the same value. So now so epsilon dash is this. Okay, this is this. So which is also the same as epsilon 2, right? In this case, which is for the second. When I say 2, I basically mean this one. So 1 is essentially for this one, 2 is for this one. Okay. So this one is the same for epsilon 2 dash. Same thing, right? Because they will all fall onto the same plot, right? Now, epsilon, like I said here, is this, right? Now then, in this case, however, if I use this expression, then epsilon 1 is 2 nu 1 Sij Sij, and epsilon 2 is 2 nu 2 Sij Sij, right? These things don't seem same. They don't appear same, right? Then there seems to be a contradiction, right? So let's just, be correct here. So, okay. So then this seems to be a contradiction, right? It seems to be a contradiction because if I use this, they're same. But then if I use this expression here, then they're same, fine. If I use this expression by the definition, then these are not. There's a contradiction there, isn't it? So this is a contradiction which arises. So what about it? How do we explain that? Well, the only way we can explain that is basically we say that as Reynolds number increases, right, with increase in the Reynolds number, as the Reynolds number increases, right, the effect of viscosity reduces. Effect of viscosity reduces, right? Correct? And also, as Reynolds number increases, the sizes of the eddies becomes finer, right? Such that the gradients in the velocity becomes sharper or higher or larger, right? What I'm trying to say here is, with increase, as again this increases, right? So the finer scale of the eddies, right? This finer scale of the eddies which is equivalent to steeper velocity gradients. Right? So what I'm trying to say here is, so say with the increase of, as Reynolds number increases, the effect of viscosity, right, here, effect of the viscosity, right, is less, fine, but then this increases correspondingly, right? So therefore, this increases correspondingly. So in effect, what happens is that these two can be sort of said to be similar, right? So if the gamma here decreases a little bit, then the Sij, this part is increasing correspondingly, so that the value does not change, right? So similarly for epsilon 2 dash. So that is where we essentially going to sort of cross this out, and basically we'll say that these two are this. Okay, so I think that's all I have actually till so far. We're going to start to talk about turbulent boundary layers, and then we'll start looking. And that should give us some more information about length scales, frankly speaking. Right now that we're going to talk about boundary layers. Okay, so yeah, so I mean that's all I have, and that. I think that should take care of a few things that I wanted to talk about. So I think the concepts of the viscous dissipation and the production, right? Mean of the rate of strain, right, which basically relates to the mean component of the flow, turbulent flow. Mean of the fluctuating part of the strain, rate of strain, which is basically contributed by the fluctuating part of the flow, right? And it is found that as far as viscous dissipation is concerned, the mean part of the flow contribution is inverse to the Reynolds number. So if you're going to talk about high Reynolds number, then this you could sort of ignore that. So the majority of the contributions actually comes from the fluctuating part of the turbulent flow, right? So I think these are things that we sort of learned and kind of revised, I guess, took a relook at from the last class. Okay. Okay, so I mean that's all I have, and we're going to start a new topic in the. Okay, one more thing is that so we are doing a lot of things, which is sort of playing around with the equations. We're trying to take the mean component of the velocity, mean of the energy equation. We take just the equation itself. We integrate that equation, and we look at that equation in several different ways, and we are able to make sense. The viscous dissipation is making sense. The production of it is making sense. And this I find very interesting. Actually, the way we write here, we develop these two equations, and then we basically say that this is production is taking away energy from the mean part of the flow and adding it to the turbulent part of the flow. Okay, so we're doing all this, but the point is I still am at a fix because there is just too many things to consider if I have to calculate, if I have to quantify all these things, and how do I do that? And whether doing it at a particular location of it, because everything is so random and so unsteady that if sure I can calculate this over a time space, then what sort of calculations do I need, what sort of data do I need, where it gives me a fair picture of the turbulent flow, right, where I do not miss out on information. And that's where the answer to that is just there is no limit to that. So we bring in this whole self-similarity thing, right? So that makes our life really easier, which is independent of the Reynolds number, and we find out that how each term will scale. And we find out that that kind of simplifies a lot of things. And there was this equation, right? In this equation where we looked at this, and the turbulent part, or the fluctuating part actually, the fluctuating part of the kinetic energy, right? Now that is the part which we didn't know. It sort of, we had a hunch that yes, this also might scale with this, because this is so this was important, because on one hand we said that, this is the part which is the mean part of the dissipation. The viscous dissipation is primarily contributed by the fluctuating part of the flow, right? So then, but then how do I calculate that? And then we sort of had a hunch that yes, this is what it will be. And like I said, it was shown by, it was proven. Okay, where did I write that? I think. Okay, so these were confirmed, right, by experiments by, so these are some benchmark work which has been done, right? And finally, we also looked at this where, again, just putting numerical, trying to understand this, quantifying this, putting some math into it is also not making sense, and then we try to understand it from more of a physical process as to what exactly is happening. So because we did all this separation, the turbulent part of the fluctuating part of the flow, the mean part of the flow, etc., and then suddenly this thing was not making sense, right? And then we saw that no, there might be a more of a physical explanation for that. Okay, we'll stop there, and I think we'll start talking about turbulent boundary layers from next class. Okay, thank you.